Good morning, class. I'm Mr Ramatladi VP. I'm with the electrical students who are studying Electrotechnics N5. We are on the chapter, which is chapter 6, module 6. Our chapter is the generation and supply of AC power. Before we can be able to delve into details into the generation and supply of power, I would like just to know that your pre-knowledge pertaining to this module. Can you give me 10 types of power stations that you will find in South Africa? Yes. Matimba Power Station. Yes. Kelvin Power Station.
CDBM Power Station.
CDBM Power Station. Kendall Power Station.
Power Station.
Kuba Power Station. And Arnold Power Station. Okay?
Little Power Station.
Little Power Station. Kusile Power Station. Thank you very much, students. As you know that these power stations usually they are used for different purposes. Like for instance, we have a hydro power station in which that those stations that are using power in order to generate electricity. Can you give another type of station that you know that is used for the generating of electricity? What type of energy that is used to generate electricity? Like for example, we have the coal power station. We are having hydro power station, solar power station, wind power station. Are we together?
Yes.
Okay. Thank you very much. Now, as you can know that, as we can recall, that the generation and the supply of AC power in South Africa, electricity is being divided into 4 divisions, in which our divisions there, we start at the generating plant. This is the generation. This is where electricity is generated, the main hub. And then from the generation, we move to what is called the transmission. The transmission station. And then from that transmission station, we also move to what is called the distribution station. And then our last, it will be what? Utilization. This is our frame from the power generating station. Like for instance, at a generation station, let's say for instance, Midubi Power Station. That's a generating plant whereby there's a system that will be used in order to generate that. An AC, in which an AC machine is called an alternator. It is used at a generating station to do what? To step up the voltage. Out again, to high voltage. Why that is done? Remember, when electricity is being generated from the generation station to utilization, now it will be transmitted over long distances. Let's say for instance, from where we are to the Palale, where Midubi Power Station is situated, the distance in which there can be plus or minus 400 kilometers. Are we together? Now, because now at that now is generated, let's say for instance, this is generated at 400 kV. Now that means that on our national grid, our transmission grid, 400 volts is being injected there so that it can be transmitted from the power generating station to the transmission station, also in which is a distance. Are we together? Now from there, the distance between that, it can be plus or minus 150 kilometers from Midubi to the transmission station. Now when it arrives at the transmission station, remember, this is a 3-phase. Now, we are talking about a 3-phase because we are also talking about the AC AC power, alternating current power. Now that is continuously being generated at a frequency of what? Of 50 hertz, which is our RSK what? Frequency. Now from here, guys, the transmission from the generating station to the transmission station is over a longer distance there. Remember, according to Ohm's law, in which it states that, what does Ohm's law state? Anyone here? Ohm's law? Yes. Current is equal to V over R, in which it says that the metallic current, now current is equal to V over I. Now what does it mean, Ohm's law? Who can define Ohm's law?
It means that the current is directly proportional to, in a closed circuit, current is directly proportional to the voltage, but inversely proportional to the resistance. When current is increased, voltage is increased, but when current is increased, the resistance will reduce.
Will reduce. But now, on that particular instance, as you are saying, the current is directly proportional to voltage and inversely proportional to the resistance. Now, for the transmission, now there are challenges that usually will be encountered here. What are the challenges? With high voltage, the more the voltage, there's also a challenge of insulation. Are we together? Now, that's why now there's cross-sectional areas of those pylons. They make them to be light because now between the generating plant to the distribution plant, now the cross-sectional area of those conductors is very small so that it can be able to do. Whereas we say that the effect, when the resistance is less, the current will be more. But now we don't need the current to be transmitted there. What we need there, we need what? The pressure. Remember, voltage is what? It is the pressure that causes what? The current to flow. Now, what is the current flow? The current flow is the flow of what? Of electrical charges. Are we together? Now in this case here, between the generation station to the transmission station, this voltage is 400 kV. When it comes in the incoming of the transmission, the voltage must be reduced from 400 kV, let's say for instance to what? To 275 kV. Let's say for instance, when you leave this transmission station, it leaves at 275 kV. It's using what? Those step-down transformers. Are we together? From this 275 kV over a longer distance from between the transmission station to the distribution station. When it comes in with 275, and then let's say when it leaves on there, now in which now it will come in with 275 from this point to that point to 275, and then can be distributed between 275 to 132 kV on the distribution system. Are we together? Now in this case here, what we also notice, we notice that now as now we are moving away from the generating plant, coming towards to our supplier or our consumer, what is happening to the voltage? The voltage keeps on doing what? Reducing. Are we together? Until when it arrives there at a distribution station. At a distribution station, 33 kV, in which can also be classified as what? Our medium voltage. And then now when we classify that on the high voltage system there, in which we say that any voltage that will be above 33 is regarded as high voltage. But depending also, this any voltage that is above 1000 volt can also be taken as a high voltage in terms of the transformers. Are we together? Now from there, when electricity leaves this distribution system, now the electricity will leave into three parts. Now it is three-phase, four-wire system, or it can also be a single phase. Now, it leaves from the distribution for utilization, whereby it goes to the main factories or our main firms, where our main firms, because of this energy, because of the demand and the need of electricity to be used, we know that when you compare the firms as well as the household, the consumption will it be the same? No. Are we together? At a household, the consumption of electricity is far lesser than compared to the consumption of electricity in an industrial area. Are we together? Hence now, when it leaves the distribution station for utilization, it will go to what? It's either a three-phase, four-wire system or a single phase. Then, from that part there, it leaves the station going directly to the what? To the pole top of the what? Of the transformer. Are we together? Now from the transformer pole top, in which is coming with the high voltage line, depending how does it live on the station? Let's say for instance, when it leaves the distribution station, it will live with, let's say for instance, with 11 kV. That means now the line that will leave from the station will be 11,000 volts. That will be that reticulation line. How to get our high voltage. When it goes there to the transformer, bottom of the transformer, it comes in with what? With that 11,000. How to get? And then now when it leaves there, depending on the transformer, let's say for example it's 11 kV, the transformer being 11 kV, and then from there it says that 400 volts. For example, now that means the high voltage side of the transformer, the incoming is 11,000 volts. The outgoing part of the transformer will do what? 400 volts. How to get? Depending on the load. Now, and then from there, when it leaves that, it will go to the pole top. The meter pole top that will find at the residential area. Now, in which now we'll find at the household. On that pole top there, it will be subdivided. Let's say for instance, 4 houses, they will be fed from one pole top. Are we together, guys? Are we together? Yes. And then from there, as it lives there, it will live from one house to another, from one house to another, and then from there, when it comes directly to the house, into the meter box. Are we together? From that meter box that is supplied by, let's say for example, the municipality or the ESCOM, when it lives there, it goes to your meter, your DB, that must be supplied. That will be supplied from the meter box. And then from there, we'll be having that electricity that has been generated from the generation station coming to your household to meet there. Can you see now the distance there from there until electricity is at your household? There are processes. Now, but in this case, our details there will also go back to a 3-phase 4-wire system. On a 3-phase 4-wire system, when it leaves the distribution station, are we together, guys? When it leaves what? The distribution station, it goes where? To the factories. Are we together? You can go to the factories. You can also go to what? Like for instance, for example, when you talk about to the factories, you can go there to go ShopRite, our malls. You can also go to Venetia. You can also go to Transnet. How to get? Given what? A 3-phase. Remember, we said that on this distribution is between 0 and 132 kV. In which that, within that, we still have 11 kV, we still have 22 kV, we still have 33 kV, we still have 44 kV, we still have 88 kV, and also 132 kV on our distribution. Are we together? Now this voltage is here, depending on the need of a customer, ESCOM can also supply that. Are we together? Now let's say for instance, the mining company says that give us 132. From that distribution station, it will go directly to what? To that mining company, and when it arrives there, it will go where? To their own substation. Are we together? Depending on what? On their need. If they are given 132, they can be able to use that 132 in order to be able to supply what is required on that. Now, let's say for instance, for traction, Transnet says that ESCOM give us 88 kV. They get that 88 kV, you go for traction. When it arrives into their main substation for that particular company, this is Transnet. And then from there, they are going to distribute that voltage according to what? Their need. Are we still together, guys?
Yes.
Okay. And then from there, hence we said that now electricity will have been generated, transmitted, distributed until it use the utilization step. At the utilization step, it is what is the main step whereby now the electricity will arrive into our households. Are we together? It will arrive to its final end product. Now in this case here, that's why usually you notice that the voltage from this generating is keep on decreasing and decreasing until it reaches your household, also in which will also be in a decreased form. Remember, as we said that for a single phase, the voltage there, we have that voltage that lies there. We can be saying that between 0 and 250 volts AC, depending on a residential area. Are we together? If with some residential area, they will be having 220 volts. Some will have what? A 230, But now, being within that range, in that, how would you get? Now, that will be for a single phase. This is the same voltage that we are using at our own households. How would you get? Because at our household, we have what? A single phase. How would you get? For a single phase, we know that we have the live and the neutral. How would you get? We are supplied with one line and the neutral is the retaining line. That will be for a single phase. Now in the factories usually they will be using mostly 3 phases. Why? Because they have more. How would you get? They will have more. Now that means now in there they will be using all these 3 lines and the neutral line. That means we have this line that is supplying. We have line 2 that is supplying. There's also line 3 will be supplying. Now another case also, this L1 can also is called R for red, L2 yellow or white. How would you get? L3 will be the blue phase, and that will be our neutral phase, in which is usually is bare or it is either black. How would you get? Now electricity has been generated and also distributed until it has reached the consumers or those people who will be required to use in that. Okay, thank you very much. As I was saying that on the generation and supply of AC power, on our CEDA bar, on Electrotechnics N5, what we need to take into consideration is the following: the effect that resistance have, inductance, and the capacitance. These are what our outcomes at the end of the day we should be able to do. Now for a single phase, now we need to look into the following, as we spoke about this. Now on that, the resistance, their effects, they are contributing factors that has an effect on the resistance of a conductor. Resistance, what is resistance? Who can define the resistance? What is resistance? We know that resistance is the opposition to the current flow. How would you get it? Resistance is the opposition to the current flow. Now those transmission lines or the overhead lines, those pylons, they will have resistance in them because they will be fed with what? With the energy. How would you get it? In which now they will be fed also with what? With the voltage. How would you get it? Hence we know that voltage, current, and resistance, they are those elements that are interplayed in that. Now, we know that voltage is like the pressure, like the pressure that causes what? That causes the current to do what? To flow. How would you get it? And then the current flow is the flow of what? Of those electrical charges through the media. How would you get it? So voltage is not current. Current is not voltage. It's just like the same as with a pump, a water tap. How would you get it? Now it has a switch there. You can switch it on or off. Now when you switch it on, that means that the water will come in depending how did you switch in. How would you get it? Now the lesser it is, the less. The more you open that tap, the more the water will also flow. How would you get it? Now in that case, we can say that voltage is the pressure, and then current is the what? Is the flow of electrical charges, in which is the electrons. How would you get it? Now in this case here, as we are saying that the effect that resistance has on this on the generation and supply of AC power, we know that there are elements that take into consideration for the resistance of a conductor. What are those factors? R is equals to the resistivity, the length divided by the cross-sectional area. How would you get it? Now what does it mean? Hence we know that the letter R, in which denotes what? The resistance of the conducting material. How would you get it? R being the resistance of the conducting material, in which that we know that our resistance is measured in what? Ohms. Next. And we also have rho. This is letter rho, which means the resistivity. How would you get it? Now the resistivity of the conducting material, of the conductor. Now we know that the resistivity of the conductor. What are the SI unit for resistivity of the conductor? Ohm meters. Resistivity of the material is measured in what? In ohm meters. And we have another factor, this is L, denoting L, in which stands for what? The length of the conductor. Are we together? Now the length of the conductor, what is the SI unit for that length? It is in meters. Now we have the length, that must be in meters. And then we also have the letter A, which denotes what? What is letter A? The letter A denotes the cross-sectional area. This is the cross-sectional area. Now this cross-sectional area of the conductor, it is measured in what?
Meters squared.
That is measured in square meters or meters squared. How you get? Now that means that when we do the calculation pertaining to resistance of the overhead line, we must take into consideration these factors. Now, provided that we know that the cross-sectional area of the conductor is given as pi d squared divided by 4. Now, whereby d is what? The diameter. Are we together? Now that will be d, the diameter of the conductor. Now, the diameter, that diameter is measured in what? In meters. Are we together, guys? Okay. Now for a single phase, as we are saying that, in a single phase now, a single phase, hence we know that it has what? 2 conductors. What are those conductors for a single phase? Yes? The live and the neutral. That's for a single phase. Are we together? A 3-phase, how many conductors do we have? 1, 2, 3. 3-phase, because we have 3 conductors. What are those conductors? N, L3. Are we together? L1, L2, L3, or red, yellow, and blue. Are we together? That will be for a 3-phase. Are we together? And then remember this, because now every generating plant, this is transmitted in a delta configuration. Are we together? From this generating plant, it is in a delta configuration. In the end or the incoming, it will be on a star connection. Now why? Because now remember, this transmission is over long distances. We cannot have a conductor that is hanging, that is not doing any job. Are we together? In order to minimize the losses, that conductor, that's why they are using delta configuration. Are we together? Because that delta will be less costly compared to star. Because also, we cannot transmit over with a neutral wire that doesn't do anything. Are we together? It will be unnecessary cost. That's why it is transmitted at a high voltage so that they can be able to minimize what? The losses. Are we together? Now the transmission of a line there, it must have minimum losses. That's why we are having those transformers that are used for what? For energy transfer. Because we know that a transformer in this case, it has what? Minimum losses because it's a static device. Are we together? Now we go back in here. I want us to look into the following. Now there are 3 types in which the conductors can be spaced. Are we together? Now there are 3 types in which the conductor can be spaced. There are 3 ways in which now the conductors can be spaced. Now what are those 3 ways? Now the conductors can be spaced symmetrically. Let's say for a single phase. Now in a single phase, overhead transmission, overhead line net. Now in a single phase, we know that for a single phase we have live and the neutral net. Now for symmetrically spaced conductors in a single phase, symmetrically spaced. Now the conductors will be spaced this way. That is the distance between them. Now, for symmetrically spaced conductor, now the conductor will be spaced for a single phase. Then, the spacing of the conductors in this, in which we have what? The radius of the conductors, in which is given as what? R is equals to the diameter divided by 2. How would you get? We know that the diameter is equals to 12 times the radius. And then from there we can also say that the radius is still the same as what? Diameter divided by 2. Provided that we know that the SI unit for this radius must also be in meters. Provided that we know that the diameter always will be in meters. That will be what? Our standard SI unit. Now, that will be for symmetrically spaced conductors for a single phase. How would you get? Now, for a three-phase spacing, for a three-phase, the spacing between three-phase spacing between the conductor for symmetrically spaced conductors. Next, for spacing between the conductors for symmetrical spacing, Now, what does it mean? Now, this is a three-phase. The conductor will be spaced like that, symmetrically to each other. Now, what does it mean? Now, the equivalent spacing of the conductors for symmetrically spaced conductors. Now, can you see that? The spacing between the conductors is equivalent. How would you get? Now, from there we see that the equivalent spacing of the conductors is equal to the spacing between the conductor. D is equal to D. Symmetrically spaced conductors for a what? A three-phase overhead line. Now, for asymmetrically spaced conductors, asymmetrically spaced conductors, the conductors will be spaced this way. Now, I want you not to confuse between the two, the diameter and the spacing of the conductors. Now, the spacing of the conductors, we use the small letter D. The diameter of the conductor, we use the big letter D. How would you get? Radius is D over 2. Now, the spacing here between asymmetrically spaced conductors, D1, D2, D3. The equivalent spacing between the conductors for a three-phase, how would you get? Is given by this formula. D equivalent is equal to the cube root of, that is D1 multiplied by D2 multiplied by D3. How would you get? That will be the spacing of the conductors in a what? In a asymmetrically spaced conductors. And then from there we also have what we call what? A regular flat spacing, a flat regular spacing. Now, with a flat regular spacing, the conductors will be spaced this way. Remember, it's a three-phase length. What will be the spacing between? This is D between conductor 1. And then this is conductor number 2. This will be our third conductor. It's a three-phase. Now, the spacing between, for a flat regular spacing, flat regular spacing between the first conductor and the second conductor, face to face, the equivalent spacing is what? D. How would you get? Between the second conductor and the third conductor, face to face, the equivalent spacing is what? D. Between conductor 1 and all the conductor here, what will be the spacing here? Is 2D. Are we together? That will be for what? For flat regular spacing. Now from there we say therefore the equivalent spacing of the conductor here for flat regular spacing is given by what? That is the cube root of D multiplied by D multiplied by 2D. This is the spacing of this face to face, the spacing between that face to face, the spacing between the all faces. Are we together? In which gave us what? D equivalent is the cube root of D times 2 multiplied by 2D. That will be the equivalent spacing of what? For a flat regular spacing. Any question there? Are we still together?